Hello, a great welcome to this presentation. Today I will demonstrate a sample calculation for the design of crane supporting beams, popularly known as a crane girder. So first, let us quickly go through the procedure followed for the preparation of this report. It starts with the collection of all important data pertaining to the crane, and this includes the collection of the rated capacity of the crane, the wheel loads, the spacing of the wheel loads, and all important requirement in the form of the evaluation of side thrust, longitudinal thrust, etc. With the crane load data in our hand, next we proceeded to the calculation of design moments and shears. The next step is the selection of a trial section for the crane girder based on the deflection criteria. With the trial section in our hand, next we proceeded for the evaluation of elastic section properties as well as the plastic section properties, including the calculation of the plastic moment of resistance. Next we proceeded to an important step, that is the evaluation of nominal flexural strength of the section based on the various criteria given in AISC 360, of which one of the important criteria is the LTB evaluation, that's the lateral torsional buckling moment evaluation. Next we proceed for the calculation of design moments about the minor axis, and finally a check for the overall strength as well as the overall LTB stability. Finally, the calculation concludes with a check for the shear. So we will start with the input parameters, of which the important is the crane load details itself. Here is shown a sample sketch for the crane girder system, and it consists of the crane that is marked in yellow, and here you will find a trolley that is moving over the crane, and then you have the crane girder that is marked in the pink color, and over which a rail is fixed on the top flange. So we have the uniformly distributed load W, that is 2.64 kN per meter. This obviously includes the self-weight of the rail along with the loads from the adjacent platforms. Then we have the maximum wheel load W, that is 169 kN. Here we have two wheels, and as you can see that the wheel loads are marked directly over here as W. And the lifted load, that's the rated capacity of the crane, is taken as 222.4 kN, and the trolley load WT is taken as 26.69 kN. Now for the side thrust, we consider it as 20% of sum of the lifted load and trolley load, which is shared equally between all the four wheels. Accordingly, H is taken as 0.2 into WL plus WT by 4, and as you can see that the value of H is 12.45, and it is marked on the diagram as shown here. The spacing of the wheels S, that is this spacing, is taken as 3050 millimeters, and the impact factor IF, which is used for the evaluation of the design moments about the major axis, is taken as 1.25. The location of the rail top measured from the top flange is taken as 0.065 millimeters, that is 65 millimeters. The value of E for the beam material is taken as 2 into 10⁵ MPa with a Poisson ratio equal to 0.3. The span of the crane girder L is 10.67 meters. The load factor for the dead load is 1.25, whereas that for the crane load is 1.5, and these are used for the computation of the final design actions or the factored actions for the design of the crane beam. Fine, so let us start with the design evaluation of the bending moments. Obviously, we know that for a beam that is subjected to a two-wheel load system, for the bending moment, for example, to be maximum under a left wheel, it should be placed at a distance of S by 4 from the center line of the beam. And for this critical load position, we evaluate the reactions on the beam RA and RB as shown here. For example, the right support reaction is 193.2 kN, whereas the left is 144.85 kN. And for this critical position of the wheel loads, we evaluate the maximum moment under the left wheel load, that is Ra into L by 2 minus S by 4, and this is calculated to be 62.31 kN. Next, as discussed, we also include the impact effect, and the impact component is calculated as LF minus 1 into MW, which evaluates to be 165.58 kN meter. And then we have the moment to be calculated due to the dead load, that is, we assume that this moment is approximately equal to the moment at the center, that is WL square by 8, and that's equal to 37.57 kN meter. And finally, we calculate the factored major axis moment under the left wheel as MRX is equal to gamma DL into MDL plus gamma CR into MW plus MIMP, and this factored major axis moment works out to be 1288.8 kN meter. Next, we need to calculate also the minor axis moment. For this, first we evaluate the ratio of the side thrust to the maximum wheel load. R1 is equal to H by W, and this works out to be 0.0737. And then the design minor axis moment is obviously obtained by scaling down the maximum moment under the left wheel load, that is MW, that is finally obtained as 1.5 into 0.0737, that's a scale factor, into 62.31, that is equal to 73.21 kN meter. So this is all about the computation of the design bending moments about the major as well as the minor axis. Next, we proceed for the design shear evaluation. Obviously, we know that for the critical shear, one of the wheel loads should be placed directly above the supports, and for this configuration or the placement, we evaluate the shear at the support as W into 1 plus L minus S by L, and that works out to be 289.7 kN. Next, we also add the component due to the impact, that is works out to be 72.42 kN, and the dead load component on the shear is WL by 2, that is 14.08. Finally, we evaluate the factored shear of the support as 560.78 kN. So thus, all the design values of the bending moments as well as the shear is in our hand. Next, we proceed to a critical state, that is, we go for or proceed for the selection of a trial section of the crane girder based on the deflection criteria, and this deflection includes both the vertical as well as the horizontal. Now, for simplicity, for the calculation of the vertical deflection, we place the wheel loads symmetrical to the center line of the beam so that the calculations can be done using the standard formula in our hand. Please remember that this underestimates slightly the deflection, and we use an allowable vertical deflection limit of L by 600. For this configuration, we know that the maximum bending moment, that is the maximum deflection under the wheel load, will be W into A into 3L square minus 4A square divided by 24 EI. Accordingly, imposing a vertical deflection limit of L by 600, we evaluate the minimum required moment of inertia about the major axis as Ix minimum is 600 into WA into 3L square minus 4A square divided by 24 EL. Substituting the various values, we obtain this minimum requirement of Ix as 0.0214 meter raised to 4. In a similar way, we also calculate the minimum requirement of moment of inertia about the minor axis using a limiting value of the horizontal deflection of L by 400, and this works out to be Iy minimum is equal to 400 into HA into 3L square minus 4A square divided by 24 EL, and that is equal to 0.00105 meter raised to 4. Remember, this is the minimum MI requirement for the top flange. Accordingly, for the entire beam section, we evaluate the minimum requirement of the total MI about the minor axis as 2 times this value, and this works out to be 0.00021 meter raised to 4. So we have now in our hand the minimum requirement of the moment of inertia about both the major as well as the minor axis. So with this requirement in our hand, we directly proceed for the selection of a trial section, and for this problem, we consider the selection of a section that consists of a wide flange beam W610 by 217 which is provided with a top flange cover plate of dimension 381 by 12.7 mm thick. So the various section properties for the W section are provided over here. I'm not going to read each and everything. And what is more important is that here the beam and the plate material yield stress is Fy is 350 MPa, and we have a reduction factor that is as per the AISC taken as 0.9. And here you can see the tile section that we have chosen. We have a W shape, which is provided with a top flange cover plate of 381 by 12.7 mm thick. So as usual, we first proceed for determining the class of this W section profile. We know from AISC 360 that the limiting slenderness ratio for the flange, it will be B divided by 2TF, and for this case is 5.92 value. And for the web, this slenderness ratio is obviously H minus 2TF by TW, and this works out to be 34.7. So this calculated slenderness ratio of the flange and the web will now be compared with the limiting values of the slenderness provided in AISC 360. And as far as the flange is concerned, this limiting value of the slenderness is 0.38 into square root of E by Fy, which is calculated to be 9.08. And for the web, the limiting value of the slenderness is 3.76 into square root of E by Fy, that is 89.88. So we have separate slenderness check for the flange as well as the web. Next we proceed for the slenderness check for the flange cover plate, and that is B by TP, that is 25.83. And the limiting value of the slenderness for the cover plate will be 1.12 into square root of E by Fy, and that works out to be 26.77. And we find that in all the three cases, the computed slenderness limits are well below the prescribed limits given in the code. Therefore, we conclude that the selected tile section, the flange is compact, the web is compact, and also the flange cover is compact. So now, to make our computations simpler, next we are going to replace this top flange plus the cover plate to an equivalent top flange, and this is done by simply from the consideration of the total area as well as the moment of inertia. For example, for the original configuration, we have the total area that is evaluated as 13924.3 mm square, and the moment of inertia of the top flange plus plate is calculated as this value. Next, we calculate what will be the radius of gyration of the top flange plus plate, which is calculated as square root of I by A, and that is equal to 100.27. And now, if you assume that T equivalent and W equivalent are the equivalent thickness and the equivalent width of the top flange, replacing the original flange plus cover plate configuration, we calculate the equivalent width WEQ as square root of 12 into I value, that is equal to 347.3. And again, from the equivalent area concept, we have the TEQ is equal to 40.09 millimeters. So we have replaced the original configuration of a flange, top flange plus cover plate to an equivalent top flange that's having a width of 347.3 and a thickness of 40.09. And this conversion will make our monosymmetrical analysis sections very simple. So now we are ready to evaluate the elastic section properties. So I think that this do not require much explanation. This involves obviously the calculation of the total area, the evaluation of the location of the major axis, which we call as the neutral axis, which is obtained simply using sigma AI yi divided by sigma AI, and the location of the neutral axis from the bottom flange, it is calculated as 361.4 millimeters, and from the top flange it is 278.99 millimeters. With the location of the neutral axis in our hand, we can readily go for the calculation of the moment of inertia about the major axis using the PLAXIS theorem, and the value of Ix evaluated is directly given over here, and the unit is in millimeter raised to 4. So we find that the Ix value calculated is much higher than the minimum requirement of Ix that is to be provided to meet the deflection criteria. So thus we find that the vertical deflection limit is automatically satisfied. Next we proceed for the calculation of the elastic section modulus in the tension and compression flange using the normal formula S equal to I by Y, and the values are plotted over here. Next we proceed for the calculation of the MI about the minor axis and the values directly given over here, and we compare this actual MI value with the minimum requirement that is provided by the deflection criteria, and we find that the value of IY is much higher than the minimum value that is required for the deflection criteria. Thus we find that both the vertical as well as the horizontal deflection criteria are satisfied, and here is shown the section. As you can see that these are neutral axis, and the location of the neutral axis with respect to the top and the bottom flange is marked over here, and the overall depth of this equivalent section is 640.4. Remember, X is the horizontal axis and Y is vertical. Next we go for the computation of plastic section properties. Obviously this also do not require much explanation, because just like the neutral axis, for this case obviously we should go for locating the equilibrium axis, and the procedure is very simple. And for this case we evaluate the location of the equilibrium axis as 433 millimeters, which is marked directly over here. Now we know that the equilibrium axis, it divides the total section into two parts, each having an area of A by 2. Accordingly, first we locate the CG, that's the center of gravity of the area, below the equilibrium axis, and that is 345.4 millimeters. Next we proceed for the location of CG of the area above the equilibrium axis, and that works out to be 146.95. So with the location of the CG of these two areas, we can readily proceed for the calculation of the plastic moment of resistance of the section about the major axis using the formula Fy into AF by 2 into YBR plus YAR, and this works out to be 2796 kilonewton meter. So remember, this is an important parameter, that's a plastic moment of resistance of the section about the major axis, that is approximately 2800 kilonewton meter. Now we can evaluate the plastic section, total plastic section modulus about the major axis as MP divided by Fy, and that is 0.00799 meter cube. Fine. Next we go for the calculation of an important parameter, that is nominal flexural strength Mn, and as per AISC 360, the value of Mn is given by the various failure mechanisms. The first one is the compression flange yielding, and for this we need to calculate a number of parameters. For example, here there is a parameter known as HC, that is 2 into YT minus TEQ, that is evaluated as 477.79 millimeters, and we have a parameter IYC by IY, and I am not going to explain all these parameters because you can refer directly to the code. And then there is another parameter HC by TW, that is 28.96, and the values of these two parameters will decide an important factor known as a web plastification factor, RPC. And as the parameter P1 is greater than 0.23 and P2 is less than lambda PW, the web plastification factor RPC is calculated as MP by MYC. Accordingly, the yield moment in the compression flange MYC will be Fy into SXC, and this is calculated to be 2901.67 kilonewton. And accordingly, we have RPC, that is the web plastification factor is MPX by MYC, and that works out to be 0.964. Therefore, we find that the nominal flexural strength Mn of the section from the consideration of the compression flange yielding is Mn1, that is equal to 0.964 multiplied by 2901, and that is equal to 2800 kilonewton meter. Next, we proceed for an important evaluation of the MN based on the lateral torsion buckling. So for this case, first we go for the calculation of the effective radius of gyration for LTB, that is taken as RT is equal to ITF, that's for the top flange, that's 100.27 millimeters. So for the LTB considerations, we need to evaluate two important lengths, that is known as LP and LR. So here LP is the limiting laterally unbraced length for the limit state of yielding, and this is evaluated as 1.1 into RT into square root of E by Fy, and that is equal to 2.6 meters. And obviously in our case we know that the unbraced or the unsupported length of the compression flange is 10.67 meters, which means that the limit state of yielding cannot be taken for the computation of the MN value. Next, we proceed for the ratio of the elastic section modulus, that is SXT by SXE, and that works out to be 0.772. So as this ratio is larger than 0.7, the nominal compression flange stress above which the inelastic buckling limit state apply is taken as FL, that is equal to 0.7 into Fy, that is equal to 245 MPa. The distance between the flange centroids is next calculated as H0, that is H minus 2T of plus half of Ti plus Teq, that is equal to 606 millimeters. Obviously, I don't want to explain all these parameters in details because it takes away a lot of time, and it's better that you directly refer to the code. Next, we proceed for the calculation of the torsional constant J using the standard equation, and this works out to be 10691250 millimeter raised to 4. Next, we proceed for the calculation of an important parameter, that is limiting laterally unbraced length for the limit state of inelastic LTB, that is marked in the code as LR, and this is computed using this equation, and that works out to be approximately 12.3 meters. So remember now that the R value of LB, which is equal to 10.67 meters, it lies between LP and LR, which means that the nominal flexural strength is governed by the so-called inelastic lateral torsion buckling. So fine. So now we can readily proceed for the computation of the so-called nominal moment capacity based on the LTB as CB into RPC into MYC minus RPC into MYC minus FL into SXC into LP minus LB minus LP divided by LR minus LP, and this works out to be 2161.44. Now there is also another limit state prescribed by the code for the calculation of MN. So but this limit state of compression flange local buckling do not apply in our case as the flange is compact. And finally, there is one more mechanism, that is the limit state of tension flange yielding, for which we evaluate the Webb plastification factor as 1.25 and the corresponding MN as 2796.64. So from all the four mechanisms that govern MN, we find that it is a LTB that governs our design checks, and the corresponding nominal moment capacity is 2161.44. So here, as you can see, that on the left is provided a sketch provided in the code that shows the variation of the unbraced length with the corresponding nominal flexural capacities. Okay, fine. So with all these MN values, we calculate now the required nominal flexural strength as the minimum of MN1, MN2 and MN3, and that works out to be 2161.44 kN meter. Therefore, we conclude that it is the LTB that governs the flexural strength. So here is provided a calculation for the design minor axis moment. Obviously, we know that the minor axis moment is caused by the lateral thrust that is applied at the rail top. And remember, here we don't go for a detailed calculation for the torsion. Instead, we calculate all the important quantities regarding the top flange bending moment by shifting this thrust H from the top of the rail to the shear center, as shown over here. And remember that for the computation of the design minor axis moment, you need to first of all locate the shear center marked as SC over here, and this is computed using the parameter alpha, which is provided over here, 0.368, and accordingly we calculate the location of the shear center as 397.2 measured from the bottom flange. Now how do we proceed? So we know that the total thrust H per wheel is 12.45. So obviously we have the moment at the shear center as we move H from the top of the rail to the shear center as HC into HR plus YT minus Y0, and that evaluates to be 3.84 kN meter. And remember that the side thrust H and this moment we convert this into an equal and opposite couple that is resisted by the top and the bottom flange, and the thrust that is acting at the shear center, it is transferred to the top and the bottom beam by the simple beam analogy. Accordingly, we evaluate the moment at the shear center that is transferred through the push and the pull of the beam, the thrust in on the top flange as 14.2 kN meter, and the thrust obtained from the horizontal H as well as the push and pull effect, the total is 14.2 kN. And now we calculate the total design minor axis moment in the top flange by just scaling our wheel axis moments, and this works out to be 83.48 kN meter. So the moment of resistance of the top flange, remember that all the effects due to the lateral thrust will be resisted only from the consideration of the top flange. Accordingly, we will calculate the moment of resistance of the top flange, and that works out to be 422 kN meter. So fine. Now we know that our section is subjected to both a major axis moment, that is from the wheel load, and also a minor axis moment, that is essentially from the lateral side thrust. So we need to compute a interaction between the two moments, that both the minor as well as the major axis moments. So the first one is the check for the overall strength, wherein we will consider only the plastic moment of resistance, and this ratio works out to be 0.732. And then we have the check for the LTB moment, wherein instead of the plastic moment we consider the Mn value, that is the nominal flexural strength of the section, and from the LTB consideration we find that the ratio is much more critical, 0.882. Therefore we find that the assumed section passes the overall strength as well as the LTB stability checks. And finally we have the check for the shear, and the calculations are very simple, wherein as per the code provisions we know that the design shear strength is given by 5V into 0.6 Fi into the gross area of the web, and we have got a parameter CV1 which is calculated as 1, and this is based on a lambda limiting value which is 2.24 into square root of A by Fi, for which alpha V is also 1. Substituting, we find that the shear capacity of the section is, or the shear strength of the section is 2 to 18.95, which means that the utility ratio for the shear is the actual design shear 560 divided by the shear capacity, that's 2 to 18, and that's 0.253. Therefore we do not have much issues from the shear. And thus, to conclude, we have verified the section for basically the moments, which is basically involves a detailed calculations on the LTB, then the verification of the section for both the vertical as well as the horizontal deflections, and finally a check for the shear. So I would strongly recommend you to go through all the AISC 360 provisions while going through this video. So as usual, thanks a lot. Please go ahead and subscribe to the channel, and if you have any comments, please let me know. Have a nice day. Thank you very much.